you have in this class of materials transitions from a paramagnetic metal to a paramagnetic insulator to a ordered insulator, or from a paramagnetic metal directly to an antiferromagnetic insulator. Now, if we look at the crystal structure, what we see is that in the metallic state, we have one non-equivalent nickel site. But once you go across the transition from metal to insulator, some octahedra expand, so they increase their volume, some of them contract. Now, based on the simple models of bond valence model, we can compute what are the expected, let's say, valences. And what we find is that the side which basically contracts, you have basically charge difference, which in this case is around 0.3 electrons. That's what we see from this bond valence model. And this is the charge which is transferred from the contracting side to the expanded side. So this is I could say, phenomenological model. Now, the next compound which I worked on, and it's interesting, is silver nickel oxide, where at high temperature we have a layered structure, nickel oxygen octahedra separated by silver. At high temperature, again, we have only one non-equivalent octahedra. But once you lower the temperature, we see the same thing expanded and expanded, which you call here nickel 1, and contracting nickel 2 and nickel 3 sides. This is octahedra. And again, we can think that at high temperature, we have nickel 3 plus, and then 3 sides of nickel 3 plus at high temperature, they go to nickel 2 plus and to nickel 3.5 plus. In this case, the system is metallic at high temperature, and once you go across the transition, it's becoming like a bad metal. Now, the next compound which I looked at and I want to mention is calcium iron oxygen 3, where again, what we have at high temperature a paramagnetic metal with one non-equivalent site. We go across the transition to an insulator, paramagnetic insulator, and then we have expansion and contraction of the octahedra. And I'm coming and do the bond valence sum, and then I have iron 2 plus at high temperature, but once I go across the metal to insulator, I get iron 3 plus and iron 5 plus. So basically, in all these compounds, what we have in this class metal to insulator transition, calcium iron oxygen 3 metal to insulator transition, here metal to bad metal. All the crystal structures have some associated with them, some expansion and contraction of the local nickel environment. And then if you apply the bond valence model, we get some charge disproportionation. And all this is fine. But now experimentally, and I want to mention that in my thesis, I was an experimentalist and did many experiments. One method to probe actually this charge disproportionation is the method what we call resonant X-ray scattering. Now, before going to resonant X-ray scattering, in normal scattering where you don't have any energy loss, which we call diffraction, what's happening is we have the crystal, we send the incident X-ray, and then we measure some particular angle where you have interference, and then we get peaks, diffractogram or peaks related to the structure as you see here. And then by trying to fit or to model the data here, we end up with the crystal structure which I just showed you. So we do diffraction at high temperature, at low temperature, we get the structures. But now, an interesting method called, as I said, resonant X-ray scattering is the one where if you have a peak which in normal diffraction is forbidden, then if you go and change the energies, keep the same diffraction setting, but change your energy, what you do, your energy at some point will match a transition from a core level to some empty states above the Fermi level. So in this case, because we work with nickel ions, you have a transition from 1s to 4p, which you call K-edge. And now if you look at what we call forbidden reflections, for example, 109, because of the scattering condition, has no intensity as long as we are away from this transition, and is zero intensity. But once we change the energy, keeping the same diffraction setting, you change the energy, you see that close to the edge of the 1s to 4p, we start to have some intensity, which again goes to zero when the energy is larger than this transition. So this is what we call forbidden reflection. We also have other reflections, like you have here 105 and 205, reflections which are finite at energies away from the resonance, but once you cross the resonance, you have some change in the intensity. Of course, if we look at the reflections which have no nickel contribution, since we change the energy to probe this transition or this edge, these reflections are basically energy independent. So this is how you do this kind of experiment. And if in the experiment you probe a certain edge of a certain eye, like in this case nickel, if you see change in this intensity, you associate this and say I have charge disproportionation. Now, moving forward, what we do is basically looking at all these reflections, Bragg reflections. You can model them with this mathematics. But in the end, what we extract by using the formula and the data, we extract the difference between the sides of what we call anomalous scattering factor. So anomalous scattering factor, or the energy-dependent scattering power of each ion, we call it has a real part and an imaginary part. And here we extracted these terms from the data for silver nickel oxide. And now the fact that we have a difference of these curves, which are called edges, of these edges, because of this term, we say, okay, we clearly have charge disproportionation. This is what we do experimentally. Now, if one wants to get out what is the charge actually, which comes out from this edge, there is an empirical plot where people have measured many compounds, which we knew exactly what is the oxidation state. And then we have a plot of oxidation state versus the energy shift. We look here, we have about 2.5 electron volt shift. You go 2.5, and we end up with difference of charge disproportionation of 1.6 electrons for this compound. And if you do the bond valence, the difference from 2 plus to 3.5, it's roughly the same. So the experiment in this case confirms very well that we have charge disproportionation in silver nickel oxide. The only problem which I have here is that the way I'm thinking, or one way of thinking about charge disproportionation, is that you have different charge around the ion. But as I mentioned previously, this compound is always metallic. So something needs to be improved, or maybe we have to find another explanation how to explain what's happening in this compound and others where you have charge disproportionation. Now, just to give you a quick idea of how to interpret basically this shift, think that in the high temperature phase, all the nickels are the same. So basically, if I take two nickels from the high temperature phase, they are equivalent. 1s has the same energy position and the 4p have the same energy position, then the edge or the transition is the same for both of them. If it's the same for both of them, I have no intensity is 0. Now, if I assume that I have just expansion of the octahedra with respect to high temperature, for the site which expands, because now the atoms are moving farther away, the 4p states are lowering themselves in energy. 1s is not affected because I'm not changing any charge around the nickel one or the nickel ions. For the site which contracts, because I have now shorter bonds, the 4p moves up. So basically, by using this kind of interpretation, which is usually used for resonant X-ray scattering, I see that if I have no charge disproportionation, but just change of the environment, I can have a difference in the edge. Thus, I can interpret this as a charge disproportionation. Now, if I'm taking the other case where I assume that I have no expansion, but I have charge transfer from one side to another, the site which has more charge, which goes from 3 plus to 2 plus, because I have now more charge in the d orbital, this charge has some probability close to the nucleus, will screen the 1s, so 1s is less bounded and it moves up in energy. For the one where now I have less charge, is less screening, this one will move closer to the core. So basically, in this case, if I have charge disproportionation, but no change of the local environment, so no effect on the 4p, again, I have a different edge. If I combine these two effects, which I believe happens in silver nickel oxide, I'm getting basically quite a large shift. And experimentally, the shift is 2.5. Now, if we do DFT on top of this, by using some tricks, assuming a ferromagnetic state, although in reality, the system, it's a paramagnetic metal, I get basically core shifts of 1 eV. The 4p now, here it's a bit of discussion, but it's about 1.5. So in reality, I get a shift, even from DFT, equivalent with my shift, which I get from the experiment. But if I look now at the charge around the ion, from DFT, the charge difference is basically very small, 0.0 something. So experimentally, I show there is charge disproportionation. I'm doing some DFT, and even if the system is metallic, I can still interpret this as some kind of charge disproportionation, although it's a bit strange because the system is metallic. Now, moving forward to neodymium nickel oxygen 3, where you have a metal to insulator transition, people have done measurements of the same kind of measurements to look at forbidden peaks 0 and 5, it's here, and 105. And they also observe this change in the intensity as you go across the edge of the nickel ions. I'm mentioning that this measurement is in the insulating state where you already have expanded and contracted octahedra. Again, extracting these anomalous factors as a function of energy, we see that there is an edge shift. I go back to the plot, taking the edge shift, I'm getting a charge disproportionation of 0.2 electron volts from the measurements. If I do the bond valence, I get 0.3. So again, there is a good agreement between the simple bond valence model and the resonant X-ray scattering. And in this case, I can understand or I can accept this kind of charge difference because now I'm in an insulating state. But still being a bit puzzled, but why do I see that kind of difference in a metal, the same kind of different insulator? I wanted to look at these compounds with a different method. The method which I'm using, it was developed at Rutgers by Christian Haule. This is the webpage of the code. We have here some tutorials. We are doing summer schools about this. If somebody has questions, you can sort of do structural relaxation, finite temperature, or study the electronic structural interplay, phonons due to Bartholomew Monserrat at Cambridge Engineering, optical conductivity, resistivity, magnetism, quite a lot of things. Now, the advantage of this method is that it bridges basically the gap between the free electrons, where you're thinking about band-like, and atomic limit, where you think about mode-like. So you can see in the same compound, you can have metallic orbitals. In the same compound, on the same atom, you can have metallic orbitals and insulating orbitals. And this is what we call orbital selective state. Also, DMFT works at finite temperature. It describes properly the paramagnetic state where you have a fluctuating moment, something which DFT cannot do. This is a method which I worked for a few years on. I was at Rutgers. I like the method, but there are many methods which can do similar things. So I use this one because I like it, but I want to emphasize that there are many other methods which can do what you're doing with this method. Now, one interesting thing here is that if I have metallic, I can have a metallic state which is weakly correlated or strongly correlated, but you can also have an insulating state. Now, the insulating state can be open due to correlation. So I have one orbital, it's occupied by one electron, and it takes a lot of energy to bring the other one, thus I'm opening the mode gap. And the signature of mode gap in this kind of language is that once I look at the density of states, if I have a pole in self-energy within the gap, then I'm saying this gap is opened by correlations. If there is no pole, then what's happening is this kind of gap, it's band gap, and happens due to hybridization or covalent interactions. So, I mean, I can talk more about the method if somebody's interested, but now I want to move on. So let me show you the calculation for neodymium nickel oxygen 3. There are a lot of interesting questions we have posed in this compound, and I have studied actually now more recently the whole phase diagram, but what I want to show you here is experimentally, we know that at high temperature, you have only one non-equivalent site. I'm lowering the temperature, I get one expanded, one contracted. If I look at the electronic properties, at room temperature, the system is metallic. If I'm looking at the distorted structure, this one, I see an insulating with a gap which agrees with the experiment. So once I saw that I can explain the electronic properties, which are in agreement with the optical properties, I also looked at the type of electronic properties on each site, but I went further and I said, let me look to see what's the mechanism of this transition. So what I'm seeing is that basically, if I look at the hybridization from high temperature to low temperature, for one site which expands, the hybridization is decreasing. For the one which contracts, the hybridization is increasing. And now thinking of the fact that I should have bond, based on bond valence model, I have this charge disproportionation, I started to look at the charge around my two nickel sites, expanded and contracted. So first I looked at this, see this is nickel inside of octahedra, so I have EG and T2G like orbitals. EG are completely filled, and I looked at the EG sites. So what I'm seeing, if you look now at this line here, blue and green, I'm seeing basically that blue and green, once I go in the distorted structure, the difference is 0.1 electrons. If I look now at the total D shell, I'm getting a bit smaller difference, still like 0.08 or something like that. But now if I look at the difference between EG, which is the blue, 3D orbital, which is green, or the total atom, I see that in reality is very small charge difference within my model. And for the total atom, it's 0.02, which basically is the error bar of the method. So now the question is, okay, I don't have here any charge disproportionation in my calculation or in my model, but I know that bond valence gives me this. The resonant X-ray scattering gives me a difference of charge disproportionation. So I was asking, did I did something wrong or what's happening? So then the next step was, okay, let me try to go back to my electronic properties. And since I saw from my electronic properties that the expanded octahedra behaves like Mott and contracting like band, if I assume this type of physics on energy axis, let me compute the signal which I measure. So this is the way we computed the tensor, have the 1s, 4p states, and then with the circles here, we have the data, external data for 2 reflections, and with solid line, we have the calculation. So what we found is that we can explain the external data without invoking any charge disproportionation. All we have to invoke here is different electronic properties on site. In other words, the way I'm seeing this is that at high temperature, I have basically expanded octahedra and metallic system, but once I go at low temperature, the site which is expanded has 2 electrons into the EG orbital, and then I'm calling this Mott-like, because there's also correlations. If I look at the contracted one, I still have 2 electrons but from the nickel, but I have also 2 from the oxygen. So this one, because of this hybridization, becomes band-like. So in other words, I can explain the resonant X-ray scattering experiment by saying that on each side I have different type of physics without invoking any charge disproportionation. And this kind of state, it's termed in the literature site-selective electronic states. Now, the bond valence model starts from nickel 3+ and goes to some charge disproportionation. Of course, well before we did this calculation, people realized that for rarest nickelates, nominally, you would say that is D7, and then you have octahedra, 1 6 electron in T2G, 1 electron in EG. But to describe the physics, they had to invoke a different terminology, which is called negative charge transfer material, where at high temperature here, I have a D8 configuration, but a hole on the oxygen. And now what's happening is once I go from here there, if I take 2 atoms where I have D8 and 1 hole, it goes to D8 and no holes. This is what I call Mott in my language. And then the other side, it's D8 plus 2 holes on the oxygen. And this is what I call band in my language. Now, because I have 2 holes, this oxygen, these ligands will bond closely to the nickel. Thus, I have a smaller environment here and a larger environment there. So what I'm showing now here so far is that by using this language, I'm introducing that each time when you have charge disproportionation in the classical or empirical view, or in this phenomenological view, is nothing else than if you look on the energy axis, you have different type of correlations. In this is Mott, and here for the contracting is nothing else but band, no correlations. Now, if I look again, and if I go further and look at the next compound, calcium, iron, oxygen 3, at high temperature, I have 1 non-equivalent site. I'm going and I have 3+ and 5+. I did electronic properties. I looked at each character of the orbital. And again, I can, instead of using D4, which we expect from the bond valence, again, here you have a negative charge transmaterial. You can describe the system as D5 plus a hole on the oxygen. And when you expand, you have a D5. When you contract, you have a D5 plus 2 holes. Now, if I do my calculation with DMFT and I look at the language, I see that at high temperature, I have the EG and part of T2G metallic. Surprisingly, I'm finding an orbital which is Mott, but still the system is metallic. Now, at low temperature, what I'm finding that the side which is expanded, it's all Mott, so I have a defined configuration. But the one which is contracted, T2G is Mott, and EG, I basically have these electrons coming from oxygen. So I have a D5L2 configuration, so this is band. Now, this one compared to nickelates, as is then in nickelates, these sites are completely filled. Here they are Mott. So again, in this compound, instead of thinking in terms of this charge disproportionation or this phenomenological way, I can come and see that I have some orbital selectivity here because some orbitals are metallic, some are insulating. And this one goes, because of electronic correlation, into one which is perfectly Mott and one which is Mott plus band. Again, a different view of charge disproportionation. Now, which I showed you, and in silver nickel oxide, I haven't put the results here where I'm writing them up. What's happening is that the side which expands, it's correlated. The one which contracts, it's less correlated. Again, the one which expands and is correlated develops a local moment, which was seen experimentally. The one which contracts and becomes more metallic is like a simple metal, and it doesn't develop any local magnetic moment. Now, here we looked at the charge order, or charge disproportionation, and we saw that each time when you have some charge disproportionation, you see some interesting electronic states where orbitals have different character. But at the same time, the resonant X-ray scattering can be used to look at systems where you don't have charge order, but you have Young-Taylor distortion, or you have orbital degeneracy, and once you lower the temperature, you get some order of the orbitals. And I have done, this is well known in lanthanum MnO3, bismuth MnO3, you have orbital order at room temperature. The way you know it's orbital order because you have forbidden peaks which appear once you go the resonance. And our question here is, let's try to see how does this orbital or Young-Taylor or metal to insulated to metal transition looks through our method. So if I look at lanthanum MnO3, at room temperature, basically, I have an insulator where it's manganese inside an octahedra. I have here a Mott gap. Here I have a band gap. If I increase the temperature, Mott gap doesn't change, band gap changes. And once I go in the high temperature phase, where I have no orbital order, here I have the order parameter, what's happening is EG goes metallic, but E2G stays insulating. So we call this orbital selective state. Now, the melting of orbital order, which was understood phenomenologically, here we term it as being going from an insulator to an orbital selective state. This was just to cross-check our method that we understand how Young-Taylor behaves in DMFT. And then we went to bismuth MnO3, where because of the bismuth lone pair, you have two non-equivalent sites. And then if you look, again, you have forbidden peaks appearing, but as a function of temperature, we have something strange, this kind of shape. Now, looking at the room temperature DMFT, we have both sides being insulating. And this is what was also termed before from resonant X-ray scattering or phenomenology. Now, once you increase the temperature, what you observe is that the site which hybridized the lone pair becomes metallic, but the other one still stays insulating. So in other words, this one we can interpret like partial orbital melting, and we have signal. We see that the signal drops, but not completely. Now, if you increase further the temperature will kill this band gap, then these two sides are the same, both metallic, and now you have to increase the symmetry because both sides are the same. And again, you have EG metallic, T2G insulating. Thus, in bismuth MnO3, you have an insulated to metal transition from here to there with partial orbital melting. And at the next transition, you have a structural transition going from monoclinic to orthorhombic. In conclusion, what I'm showing, or the message I wanted to send today is that each time when empirically we see some charge disproportionation, we can explain it phenomenologically by using this negative charge transfer. But if you do numerical calculations like DMFT, we see that in reality, you have either sites orbital selective, so some orbitals are metallic, some are insulating, but the insulating can be Mott or band. The interesting part is that, for example, when you increase the temperature or change the structure, this Mott gap or band gap can decrease, can collapse, so you can have a continuous picture of what's happening across a transition where we claim that we have charge disproportionation. And the other thing I want to mention is that I'm using DMFT because I spent a lot of time on it. I developed it, I do summer schools, but a lot of these things can be done also with other codes. So I'm not really selling the code, but from my point of view, since I'm used to it, I consider it the best. That's all I want to say today. Thank you. If you have any questions,